Welcome, everybody. I hope you can hear us well. I'm really excited to be here today to talk about hardware root of trust with Google Cloud IoT Core and Microchip, one of our great partners for a bunch of security products and other connectivity products. My name is Antony Passemard. I lead the Google Cloud IoT product management team, and I'm with Nicolas Schieli from Microchip. Nicolas, you want to introduce yourself?
Sure. Thank you, Antony. Hello, everyone. So my name is Nicolas Schieli. I'm managing the marketing and application engineering team for Microchip for the Secure Products Group.
Great. Thanks, Nicolas. So today, a little bit of an agenda. We're going to talk about why security matters for IoT. It may be obvious to a lot of you, but definitely something to remind people. We're going to talk about what does root of trust mean really for IoT devices, and that's an important concept that we're talking about in that webinar. So it's something really interesting to look at. We're going to talk about the difference between hardware and software security, a big debate for IoT, and one of the key points we're addressing in that presentation. Then we're going to look at Cloud IoT Core, just get a little bit of an overview of the new service that we launched fairly recently, something that is currently in beta, and you'd want to learn more about. Then we'll look at a secure flow between Google and Microchip, which is really key to the partnership we have together between the two companies. We're going to talk a bit about firmware validation for IoT devices. Very important if when you want to make sure what's running on the device is what it's supposed to be running. And then how do you get started with all of that? So without further ado, I'll pass it on to Nicolas to talk about Microchip and the security solutions that they have.
Thank you, Antony. So just a few words. So Microchip is a $4 billion revenue company headquartered near Phoenix in Chandler, Arizona, and we are primarily focused on microcontroller, high-performance microcontroller, digital signal controllers, microprocessors, a lot of mixed-signal analog interface and security solutions, also clock and timing solutions, and obviously wireless and wired connectivity solutions, and then finally also EEPROM and flash memory solutions. Overall, Microchip, with the security solutions, we've been very active in the IoT space to try and simplify how we can secure IoT devices and make that connectivity secure. So let's look at why IoT security is that important. So if you're looking at what happened recently, there is clearly an acceleration of the number of attacks that are happening in the world, typically targeting IoT devices, but not only. Overall, basically attacks are becoming more and more sophisticated. And one common thread among most of those attacks is the fact that it's all about the key material or the confidential material that are in the devices that is typically too close to the software. So the software ends up leaking out some of that critical material. So in that context, we work very closely with Google on trying to find an easy but very secure solution to secure IoT devices. So looking at, that problem basically, we're looking at having basically a hardware root of trust for connected devices. And what is hardware root of trust? So it basically, you need to have two basic concepts. So you need to have a verifiable, trustable, and unique identity for a connected device. But you also need to make sure that, which basically allows you to verify that the device that is connecting to the service is the one that you're supposed to be connecting. The second thing is you need to make sure that you can validate the device firmware and make sure that what is running on the device is indeed the genuine firmware. So device identity, it's essentially a little bit like a birth certificate for each device. So it needs to be unique, verifiable, and trustable. So it's based on cryptographic key pairs. So you have one private key and a public key. They are mathematically related. And you need to, so the whole identity hinges on the fact that the private key remains private during the whole lifetime of the product. So if the private key is ever disclosed, that means someone can abuse the identity of that device and can basically spoof the connection to the remote service. So you need to be able to verify with the public key that this device certificate is valid, and basically you need to make sure that overall the private key is always private during the whole lifetime of the product. So the bottom line is you have to have a strong isolation of the private keys from the users. You don't want any of the private keys of any of the devices to be at any point in time exposed to any of the users. You want to isolate the private keys from the software. Very often, as we've seen earlier, the attacks are really about the weakness in the software leaking out some of the private keys. So the third point is you want to make sure that those keys are never exposed during the manufacturing phase of the connecting device. So overall, the best way of ensuring all that is to make sure that the any of those keys are never in the microcontrollers that are typically not designed for hosting sensitive material.
The point number 3, Nicolas, is kind of interesting because people don't realize that there is actually a risk of exposing keys during the manufacturing process. If you're leaving your keys to your manufacturer, oftentimes in countries where IP laws may be a little different, there is definitely a risk that those manufacturers would copy those keys and create fake devices or copies of your devices that are not legitimate and can be used to connect to your architecture. That's something people don't realize.
Absolutely, especially if you end up generating keys or generating the identity of those devices on your manufacturing line. So that may become a very complex problem, and you may need to invest into securing a manufacturing line in an environment where secure manufacturing may not be that obvious or easy to implement. So looking at how we can implement a true trustable identity in the devices. So we basically have come up with a product line of devices that basically are implementing a few basic features. One is to make sure that whatever you're storing in the device, whether these are the private keys, they are securely stored in a non-volatile memory. So that memory is typically encrypted. And you have also within a cryptographic hardware boundary, so basically a boundary that prevents someone from looking what is inside the chip, you have also the cryptographic engines. So what you want to do is you want to have all those features inside the cryptographic boundary. If any of those features is outside, your security is essentially potentially compromised. Because the cryptographic engine needs to be able to have access to the private keys to be able to perform its computation. So you don't want to have to move the private key outside of the cryptographic boundary of the device. Similarly, you want to be able to have a high-quality random number generator. Without any of this, you won't have really true security. So for instance, our devices are capable of generating their own keys, and they are typically the output of the random number generator. So you need to have a very high-quality random number generator, or if not, you would end up being able to devise keys quite easily.
That's an important point here. You're saying that the random key generator and the keys and all of that is inside the anti-tampering hardware. That means that's the hardware you can't open with like a screwdriver or anything. You could not access what's inside of it. But the private key is never burned into that device. It is generated by the device itself and is never outside of it. Absolutely.
So this is a very important point. So the private key is something that never exists outside of that tamper-hardened hardware boundary. So basically, you don't want to generate your key outside and have to transfer it inside a safe. So the best way to have a good protection is to make sure that the secret is generated within the safe. So how is such device used? So basically, overall, you have essentially a microcontroller, and on the side of that microcontroller, you would be adding the crypto device that contains the private key. So the private key is generated by the device. And the microcontroller would be generating a challenge that is changing from time to time. Every time you're running that challenge request, it's going to be a different one. And it sends that to the secure element. And then the secure element uses its private key and the crypto engine to perform the cryptographic function, and the output is returned to the microcontroller. And the microcontroller then has a response from the crypto device that is verifiable. So essentially, the microcontroller will be able to verify, or the microcontroller or the remote service will be able to verify that what it's talking to has knowledge of the private key. And the device basically is like a safe. So the private key has been generated inside the device. The device is a secure element with a cryptographic boundary that is very protected with many layers of security that basically make the retrieval of the private key extremely challenging, if not impossible.
And that device is the ATCC608A here. It's a fairly small device, if I recall.
Correct. So the device is available in a couple of package options. So one is an 8-pin device where only a few pins are used. But the smallest one is basically a 2 by 2 millimeter UDFM device. So that's something that is very difficult to spot on any PCB, quite frankly.
Great.
So the bottom line is you want to be able to have this safe really secure, right? So the key is generated in the device, and you want to have hardware protections that prevent someone from being able to get the key out of the device. Because again, if I know the key, I have your identity, right? So the whole identity concept is based on the fact that the private key is private and secret. So you have in the device a number of defenses that are implemented in hardware. So you can see on this slide the differences, the obvious differences you have between a secure device and I would say a standard device that doesn't have any hardware protection. In a standard device, you will be able to see all the logic, all the memory areas. That means you would be able to quite easily, with quite standard equipment, to be able to get to the memory locations and read out the content. So the secure element, the ECC 508 and 608 devices have, as you can see, an active shield on top of the device that basically is the first layer of protection, preventing people from being able to easily access the logic that is in the device.
Great. So now we've talked a little bit about the hardware side of things, and a very tiny crypto device that can generate its own keys and random key generator, etc., and store that very securely and serve as the crypto engine. Let's look at the cloud side now with Google Cloud IoT. When we designed our IoT platform at Google, we have a lot of experience building IoT devices. All of you probably know the Google Home and the Glass and some of the Wi-Fi hardware we have, etc. But there's been a challenge across every type of IoT devices, both in the industrial and commercial world and the consumer world. It's always the same. There's a security challenge. That's what we're addressing today, on securing the device, securing the communication and the identity of those devices. The second problem is scale. It's fairly easy to connect a few dozen, a few thousand devices, a few 100,000 devices even. But when you start talking about either millions of devices or millions of messages per second to a single endpoint, this becomes really difficult to do. And this is what the experience in scaling at Google is very valuable in that area. And finally, the actionable insight is very important, because there's really no point connecting devices if you're not going to get insights out of that connectivity and out of the data. And that's really a data challenge, a big data challenge that Google is very, very good at. We have over 7 products that have over 1 billion active users a month. So we know our big data. I mean, you're probably familiar with search and Gmail and YouTube and the way we serve ads. Those kind of challenges of managing and analyzing very large amount of data is one of the core strengths of Google. So we looked at that with those core strengths and those challenges and built our IoT platform on that. So if we look at the product that we just announced, it was announced last May and then launched in beta a new service called Cloud IoT Core, So Cloud IoT Core is one new service as part of a suite that creates our Google Cloud IoT platform. It is the cornerstone of the connectivity and the device management. So it will communicate bidirectionally with devices. You'll be able to define your devices, manage them from IoT Core. But then in terms of data flow, the data will flow from IoT Core to PubSub, which is a global messaging service I'll talk about. You can trigger cloud functions, which are serverless processing units. You can trigger data flows, which are the equivalent of Apache Beam. It's the managed version of the open source Apache Beam, which allows you to do processing over windows of times, for example, over the last 20 minutes, look at all the temperature coming from those devices and tell me the averages and the bands, and if am I out of band based on an average, things like that you do in data flow. It's a very powerful tool, all managed for you. And then the data will flow into a database service like BigQuery, our data warehousing tool, or Bigtable for NoSQL. Those data will be used by our cloud machine learning engine to create models at very high speed, very high accuracy, and then those models can be used in data flow or even by your devices themselves. And we have some visualization tool in Data Studio and Data Lab more for your data scientists to manipulate the data and create better models overall. So that entire suite is really what is Cloud IoT for Google, and all those tools all of them are managed services. There's really no operations to do with those. So if we look a little bit more into Cloud IoT Core, there's two components to it. One is the bridge, the protocol bridge. We support MQTT and HTTP protocol endpoints. We have a planet scale ingestion and a planet scale consumption. And I'll talk a little bit about that in the next slide. But that's a very important aspect of our platform. We do automatic load balancing, auto scaling. It's a managed service fully. There's no auto scaling policy to create. There's no cluster size. There's no no virtual machines, no load balancers, none of that. It's an endpoint that you have in your project, in your Google project, and we will scale it up and down to your needs. If during a month you send no data or very few data, you're going to have a bill of zero. There's really no upfront cost to using IoT Core. On the other hand is our device manager. That's where you create your devices, you create all the attributes, you can create hundreds of attributes on devices. This is where you're going to have your bidirectional communication with the device, with the notion of a digital twin, and being able to set states and configuration for the device. You'll be able to have role-level access control, which is an extension of the security of the chip, and also being able to access all those features through APIs, command line, and console similarly. So when I was talking about global scale, this is a very important point for IoT Core. This is actually a very big differentiator from other clouds. Google is one of the only cloud vendor to have and own and operate its own backend globally. We own all the fibers, we own the network globally. That's how we serve ads and YouTube that well, because we have the network. And when you create a device and you connect it to Cloud IoT Core, you only need to know one URL. It's called mqtt.googleapis.com. That single URL is used across the globe to load balance traffic to the closest access points that Google has. That means that if you have your IoT Core in the US, great, but your device is in Australia, you don't need to have IoT Core in Australia. The device will automatically connect to the closest POP in Australia and use the fiber network to get to the US, to where the data needs to live. That gives us a scale that nobody can provide you. And that gives us the ability to pre-configure devices before you know where they ship. You can just say, mqtt.googleapi.com on your device, and it will connect everywhere. We connect over port 443 natively or 8883 also. So we support, we can go through firewalls pretty easily natively with IoT Core. So that's a very, very big differentiator. When the data lands in IoT Core, I told earlier that it goes to PubSub. PubSub is also a global product. That means that you don't have to think about, oh, was that data posted in Australia? Was it posted in India? Was it posted in Europe? You don't need to think about that. You'll just get the data out of PubSub through a single topic and get all the, or several you configure, and you'll get all that data in your backend for your application to be built on. So that scale that we have, very seamlessly, there's really nothing to configure for you. It's something that's very differentiating from other cloud vendors. In terms of authentication, because we're talking about security and identity here, this is an important area. So here's how we do the authentication with Google Cloud IoT Core. The device will establish a TLS session with a Google front end, anywhere, one of those 100+ POPs, and then we'll do an MQTT connect. In that MQTT connect, you have a username that is ignored, we don't use it, and you have a password. That password is a simple JOT token, a very common concept for web developers. That JOT token is signed with the private key of the device, right? The private key of the device. It is sent as the password. There is no mutual auth in the TLS stack, right? It's just sent as the password. On the receiving end of IoT Core, we take that JOT, we validate with the public key corresponding to that device that was sending the data. We'll validate the signature and that mutual authentication is established at that point. So we don't depend on the TLS stack to do the mutual authentication. That's a very important point because all we need on the device is a private key. That's it. No certificate, no big TLS stack, no dependency of the TLS stack to the crypto hardware, like the Microchip one. You don't need to have a special TLS stack for that. If you do an update of your TLS stack, it will still work. You don't have dependency in your code on that TLS stack. So that's a very important differentiator as well. Allows to have a much smaller footprint on the devices to establish quickly a secure communication while keeping the mutual authentication via the signature of the JOT token.
So this is a very important point. We have worked on a few different implementations on our side, and we've been able to have a Google Cloud IoT core authentication running on a small 8-bit AVR product.
All right. Yeah, that 8-bit thing was very impressive because I had never seen it before. Because all the stack is so small, it can actually live in the Wi-Fi module, for example, entirely in the Wi-Fi module with very little memory.
It's a standard stack, so it's pretty simple to implement.
Exactly. And then next to that, you can have an 8-bit MCU that is extremely cheap to read, read a temperature or set a few settings in the machine. You don't need a 32-bit MCU. You can just use an 8-bit MCU, and that makes the whole device much cheaper. So this is more of a visual representation of that authentication. In a typical flow, a provisioner person will create keys. A public key goes to IoT core in the device manager. A private key goes on the device. Then the device generates the JOT, signs it, sends it as part of the connect as the password. IoT core looks at it, validates the signature, and opens the connection. That's typical. But you see the flaw here. The provisioner has to create the keys, and that private key lives in the provisioner's hand and has to be burned on the device. So that's where the partnership with Microchip comes into play. The partnership with Microchip is much more secure because if you buy that crypto chip from Microchip, because the crypto chip creates its own private key inside of it, it will generate a corresponding public key. When you pass the secure element to the device, it's already programmed. It's not in a file. It's not anywhere in the hands of anybody. It is inside the chip. That chip is put on the device. The public key goes to the provisioner and is sent to the device manager to be registered. Then the rest of the process is very similar. The device creates a JOT token. The JOT token is signed by the crypto device, the ECC608, natively. There's no private key floating around. It's done inside the ECC608. And that signed JOT is passed as a password for establishing the communication. So as you see in that model, the key is never, ever exposed, neither to the provisioner, neither to the device. It's always inside that very secure element, and it makes it very easy to connect.
So in that context, many developers of connected devices may want to have their devices as part of an ecosystem that is managed. So the way to do this is to have a public key infrastructure. So luckily, Google Cloud IoT Core has the ability to, you have the ability to load your own certificate authority into the cloud. So we can assume that the certificate authority that is managing essentially the whole ecosystem of devices has done a good job of protecting the private key that comes with this certificate authority. So they are responsible for holding that private key private.
Yeah, and that certificate of authority key is on a per registry setting. So we have per project, you can create several registries. So each registry can have a CA authority that's different or similar. So you can use the same CA in different registry if you want. That's totally feasible as well.
So the private key of the CA is at the CA, and that's why you're using a CA, is because they're setting the service of protecting that private key. And then you typically have a hierarchy of CA. So you have typically an intermediate certificate authority that is below that root CA. So there's a signature in between the two. I think it's very often what we see in actual deployments. People tend to do this on their manufacturing line. And that's a big part because the whole trust in the chain depends on this second private key being private all the time. Because if someone has access to that private key, they would be able to sign certificates of the devices, right? And then basically the last level is that you have the device certificate and the private key of the device that is in a device, in the secure element, and the secure element basically is the one that has generated that last private key. So that last private key is essentially secure for the whole duration of the whole lifetime of the product. So overall, you see this chain of trust may have a weakness if the second key of the intermediate certificate authority is not correctly stored in a secure supply chain.
And that's typically in the manufacturing.
That's typically what we see very often done, right? Because that's a shortcut that you may do when you're implementing your manufacturing line. So at Microchip, we basically worked on trying to offer a solution that is very secure for the customers without having to even think about how to set up their manufacturing line. So the second key, which is the intermediate certificate authority, is something that we offer the service of hosting the client's intermediate CA private key and essentially signing the individual devices as part of our standard manufacturing flow. So you don't have to invest into a secure manufacturing flow on your side. You can buy devices directly from us that are signed by a chain that is completely trustable.
So the customer does not need a PKI at all. Microchip provides that entire infrastructure with a secure manufacturing line that's audited, that has all the certification, can be audited by customers potentially. And that means that when the customer basically just buys that crypto chip, it's all done for them. There's nothing to manage at all. They buy a crypto that is already programmed, already compatible with IoT Core, and there's nothing to do for them.
Correct. So, and this second intermediate certificate authority key, private key, is stored in our hardware security modules that are on our secure manufacturing line. So this is something that if you had to deploy that yourself in your manufacturing environment is complex. You need to have the expertise. You need to invest into the hardware, which is obviously not free, and operate this. While we have that whole infrastructure ready to go, and we're doing this in high volume today.
Yeah, it's not about just the hardware here. It's about access from people who operate in the manufacturing line, the background checks, the security audit.
It's mostly about the expertise, right? On how you operate that, how you design it to make it secure during the lifetime of the manufacturing. Now, the thing is, if you invest into that infrastructure in your backend, you basically going to be doing this investment once. So now, if you want to change suppliers, you're going to have to move all of that or reinvest. So it's quite expensive. So initially, we talked about the fact that you have to have two concepts. So we spent quite some time on the unique identity that needs to be trustable and verifiable. But there's a second concept that is very important to IoT devices. You need to have the ability to verify that the firmware that is running on a microcontroller is valid. So you have basically for this, you need to have a cryptographic key pair for the firmware validation. One, which, I mean, again, the private key that we'll use to sign the application image. So the application image that you want to run on a microcontroller will first be hashed, and that gives you a firmware digest, and you will be signing that digest with the private key that is the device manufacturer private key, and that the resulting signature is something that is appended to the application image.
So this is another use of the ECC 608. So
correct.
The first one was to store the keys to authenticate to Google Cloud IoT Core. This is with the same chip, you can actually do your firmware validation.
Correct. So basically, you need to have those two concepts implemented in your IoT device if you want to have a secure device. So this is the process to sign your firmware. But what is important is that at runtime, you actually validate the firmware. So at runtime, you have your host microcontroller with the application image, and you have the secure element, the AT-ECC 608A on the side that actually contains the public key of the signing private key. And the host microcontroller will compute the digest of the application image, will send that digest to the AT-ECC 608A, which will be able to verify that digest corresponds to the signature with its public key, and then will authorize or reject the execution of that application image. So then the secure bootloader, which is the piece of code that runs on the microcontroller that handles the start of the overall firmware of the product, will, based on the assistance of the 608A, will be able to decide whether the firmware should be running or not. Now, the important point is that if the 608A detects that the firmware that is being verified is not valid, it will essentially lock down, it will forbid the usage of the private key that is used to authenticate to Google. So that means if the firmware that is presented to the 608A is not valid, the device will refuse to generate a valid token.
Okay.
So you will essentially be offline.
So you're not only preventing the image from loading, but you're also preventing the use of that key to even connect to IoT Core, which is a second layer of security that's appreciated.
So the summary, maybe Antony, you can talk a little bit from your side what we've been able to provide together.
Yeah, this was several months of work with Microchip, and we're really happy about the results because it's very much solving a big problem. It's today having a PKI for your devices does not really make sense. Having to generate certificates. A lot of customers talk to us and they say, "How do I generate that? Where do I store them? It's a pain. It's a pain." And I think that partnership with Google and Microchip really solved all that pain because all you have to do is literally buy a crypto from Microchip, and it's all configured, all able to sign the job, able to secure the job, validate your firmware, do a lot of the security things that you literally have to do on devices, but also on a very tiny device. And I want to emphasize that this is not, in terms of cost, this is not something that's going to add dollars to your implementation. I mean, you want to comment a little bit?
Yeah. So basically, if you're buying just one device, it's basically less than 80 cents. Oh, wow. And if you're going to like 5,000 devices, you're below 60 cents. So it's very affordable.
So if you think about 60 cents at low volume, 60 cents per device to avoid having a PKI, a complete PKI, avoid having to to be in the news as one of the devices that's hacking or doing DDoS attack on the DNS servers and the internet. That's actually a fairly low price, and it's such a small footprint that you can literally add it to almost any device.
Yeah, you can always find space on your PCB to add this on the side of microcontroller.
Yeah. So the level of security provided by their partnership is very exciting. It's the simplicity is amazing, really, and it can really work with any microcontroller processor, especially because the IoT Core authentication is not dependent on the TLS stack that runs on those microcontrollers. So that makes it very easy to be compatible with any device. As long as you can have an MQTT stack or an HTTP stack, you can have a simple TLS stack just to connect to Google, and the ability to create a JOT. That's about what you need on the device. So very tiny. We're really excited about this solution today. It is available today.
It is available today, and we do have tools to get started very easily. So we have a number of hardware boards that you can purchase today from the Microchip website, and we have here a link that will be available in the presentation once at the end of this webinar. You can go to this page and you will be able to buy the hardware, and it's basically a basic microcontroller along with a Wi-Fi device and the secure element ECC608A that you can plug together in a very simple way. And we have all the source code that we talked about on GitHub. So everything is referenced on that web page. So you can download the firmware, you can modify it to your needs. And we have even some examples on how to control a fan or temperature sensor. So we have more advanced examples rather than just the connectivity.
Yeah, excellent. So those are very readily available to buy. In IoT Core, if you sign up for a Google Cloud Platform account, IoT Core has a free tier. So you can, IoT Core is charged on the bandwidth usage only. There's no notion of number of devices or number of messages. Doesn't really matter. It's a matter of bandwidth. How much data are you sending or receiving from that MQTT bridge? And there's a free tier of 250 megabyte per month that you can just use for free to get your first devices connected and tested. And after that, it's a fairly downward slope in terms of price as you go up in volume of data. So a very competitive pricing overall, only based on volume of data, not on number of devices, not on number of messages generated. So you can get started. There's two links here, cloud.google.com/IoT. You'll land on the Cloud IoT page. You'll be able to have access to the documentation, some sample codes in almost many of the common languages. On the Microchip side, microchip.com/ATECC608A, GCP IoT Core. Here you'll find the devices Nicolas was talking about. You'll find sample code as well. It's very easy to get started. And we thank you very much for your attention and participating in that webinar. We have a few questions now, so we'll go to that. One of the first question is, what is the level of FIPS offered? That's for you, I think.
Yes. So basically, FIPS, we have, so FIPS, it's not a FIPS certified device, but you have a number of things that you can do around FIPS. You can have a CAFP certification for your algorithms, which is something that we do for the 608A. That's one thing. And the second thing is you want to have a FIPS capable random number generator, which is also something that we have in that device. So we have the FIPS-based random number generator that is implemented, and we have also the newer specification for the health test. So that means the device will be verifying that the randomness of the number that is being generated is at the right level at the time of generation. Because you could have a very good entropy for your random number generator in your lab, but that doesn't say anything about what's going to happen in the device once you are in the field, different temperature, different voltage. So these are things that are addressed by the health test that is implemented in the device. So this is a new standard from FIPS that essentially tells you how to do the random number generator, and we have implemented that in the 608A.
Great, great.
Also, in addition to this, we have been working on the penetration testing with third-party labs. That gives you essentially a GIL level so that you can get an evaluation on how robust you are against known attacks. And we've been working with a lab in Europe that is really typically working on Microchip certification. And the GIL level evaluation is something that is typically one of the first steps of the Microchip certification. So the combination of the FIPS compliancy for the algorithms, the random number generator, and the proof that the penetration resistance is very high is something that we can provide to the interested customers if they really want to look into this.
Great. So the second question is around, are we going to be able to provide the presentation or provide the recorder version of the webinar? I believe this is recorded and will be available, if I'm not mistaken, so I think the answer is yes to that question. Can the JWT token be copied and used in replay attack? Does the IoT node require a RTC to provide a timestamp element? So
you don't need an RTC, but you need time. Yes. So the JWT token is valid for a certain amount of time, and you need to have time at this point. So you're going to get time from an NTP client, for instance. And so the JWT token is when it's signed, has a creation date and an expiration date. And on the Google Cloud platform side, they will be accepting tokens that are within that time frame. This is a policy-based thing.
Yeah, so to clarify, so when you create your job, you can specify an expiration.
Correct.
So first you can say my job will be only valid for 20 minutes or 10 minutes or whatever. The upper bound of that is 24 hours, and there's a little bit of I think there's a few minute lag like window around that. So no more than 24 hours, the job, but if you specify in your job that it's a 20-minute, 30-minute, 2-hour validity, then this is what the job can be used for in terms of period. But remember, you need to sign that job with the private key. So it's not only copying the job, you need to have access to the private key to sign it. Otherwise, you won't be able to use that job.
Right. So you don't need an RTC in hardware because you're typically connected, so you are able to get time.
So let me see other questions here. Is it possible to do firmware device update and then update the ATECC608A with a new hash secure boot?
Yes. So that's an important point. So indeed, the 608A has a few features that allow you to handle this use case of OTA. So basically, the 608A will, the first time you're going to be using it, will receive the hash from the microcontroller, and then will receive the signature that was generated by the private key at the time of signing the firmware. We'll receive those two, we'll validate that they are valid. If they're valid, it will store them both, right? And now, if you're coming up with a new firmware, there will be a new signature. So you're going to be passing the new digest with a new signature, and then the device is able to, if again they match, they verify correctly with the public key, will update its content with the new signature and new digest.
Yeah. There's quite a lot of questions around OTA, and somebody says here OTA are generally poorly verified today. Can I use the ECC 608 to verify the OTA for an IoT device is connected to Cloud IoT Core? I think that's
that's actually, so the 608A is an upgrade from a product that we've been shipping in very large volume up to quite recently. So we launched the 608A in November last year. Before that, we've been selling the 508A in quite large volume. But the 608A is really an improvement on a number of things, especially the firmware validation to make it simpler to be able to correctly support those OTA use cases. Also, the improvement on the random number generator, because again, now FIPS has a way, they have standardized the way of verifying that the random number is good enough at runtime. So we have implemented this.
Yeah. One of the questions is the integration effort of the root of trust with a secure bootloader high?
No, overall, so we have a few examples on our website on how to implement a secure boot. So what the scheme I've just presented, we have a few examples on our website that give you, again, example code on how to do this. So the implementation is quite simple. So the bootloader portion of the code needs to exist, right? Obviously, the bootloader is communication dependent, so it's something that could be depending on how you're receiving the new image. So that's something that we cannot really provide examples for all the use cases because they are all dependent. Assuming that you have a way of getting your new firmware into the device, then the 608A can be used to validate the firmware.
Cool. The questions are flowing. We'll try to answer all of them. Does Microchip also have application examples using PIC MCUs?
So all the examples we have on the website right now, they're using ARM-based MCUs, but we have customers using PIC devices, so we have all our libraries that can work on PIC devices as well.
Great, that's awesome. We're being thanked for the webinar, so thank you for the person who posted that. He's asking about real estate usage, and would you have a chip in the building or a wall and other collection of information on the state of that building. I mean, building use cases, just so you know, we have hundreds of buildings at Google. They're very, very connected, and we're actually implementing IoT Core to connect all of those right now, and we're looking at usage of that crypto wherever possible. But the goal of the crypto is really to be used on each device if possible, if those devices are IP enabled. If they're not IP enabled, you could have those crypto at the gateway level as well for the building. If you have that, if you have a backnet in your building, you may have some devices that won't really be able to use the crypto. That authentication can be done to a gateway that uses the crypto device, obviously. So yeah, a lot of example. We have a great, by the way, partner for buildings called Candy Control. They connect to IoT Core. They have a great partnership with Google. So if you have implementations for smart buildings, look at those guys, Candy Control, CANDI. They have great solutions for smart buildings. Can the ECC 508 also be used for Google Cloud services?
Absolutely. So the 508A, that, as I mentioned, has been in production for many years. The 608A is an improvement over that in terms of making the secure boot validation, the firmware validation simpler and be able to handle easily the OTA use case. So the 508A can do very much the same thing. So we can hold the private key that is used for signing the JOT token in the 508A, very similar to the 608A.
Great. And does Cloud IoT, Google Cloud IoT support IPv6? That's a very good question because not every cloud provider support that. So remember when I told you about the Google network that we're using? This is one of the cool stuff about building products at Google. We build it on an infrastructure that's so big and battle tested and has so many features that we just get those for free. The Google front end supports IPv6, so IoT Core supports IPv6. That's one of the beauties. So you can connect with an IPv6 protocol to the Google front end, and then from there you're on our network, you're in IoT Core, no problem there. So IPv6 is supported by Cloud IoT Core. Is IoT Core IaaS or PaaS? And how would you describe it? So IoT Core is a fully managed service. So it's not an infrastructure as a service. It's almost a SaaS if you think about it. It's an endpoint. So when you log into your GCP console, you'll see at the bottom left there's going to be a link called IoT Core. You'll go in there. The first thing you do is you create a registry. You give it a name, and inside that registry, create a device and upload your public key. That's all you have to do. And that's it. There's no configuration, nothing. Then you have mqtt.googleapis.com. That's your endpoint. As I said, it's a global endpoint. You don't have to think about where you are. You don't have to think about the fact that you're in Australia, in the US, in Europe, in Japan. Doesn't matter. We'll load balance to the closest Google front end and get that traffic to the region where you want it to be. So there's one region globally that you use to have your device manager, but the connectivity is global. The data lands into the region you choose. So a fully managed service, no load balancing policy, nothing, no auto scaling policy, no cluster, no shards, none of that, no VMs, nothing, no updates. Everything is done for you. It's a fully managed service. How Cloud IoT Core help a global corporation to scale as the number of IoT connected devices can vary tremendously across the globe? I believe that's one of our core strengths. There's two things. First, it's a managed service by Google. So we will manage the scaling up and down for you. You don't have to think about it. You can send us 10 million devices, 20 million devices. It doesn't really matter to us. You don't have to think about it. That's our job to do. And Google does that really well, as you know. Just look at YouTube and Gmail and all those other services and search and app distribution. All of that are super scalable, and that's what we use to power IoT Core. The other thing is you're talking about global scale. The cool thing about the global network we have is because when you use mqtt.googleapi.com, it is globally distributed. If you have a network of devices that is globally distributed, you will actually be automatically load balanced across the 100+ front end that we have across the globe. So you're not hitting the same front end by all your millions of devices across the globe. They will be automatically distributed, which helps a lot with the distribution of load across the globe. So we're really well architected to do exactly that, the big global corporation at scale. And I think that's all we have as question. That was quite a good number here. Please provide feedback on the webinar. There's a way to do that through the tool. We'd love to hear what you liked, what was missing, what you didn't like. We'd be happy to do another one later on. As we have updates on IoT Core, we have updates on the ECC 608 and different implementations. So happy to talk more about this. I think this is really changing the game in terms of security and IoT. It brings simplicity to our customers while keeping the level of security at the highest possible, but removes all the hurdles and works perfectly with IoT Core. So really exciting about this. And if we don't have more questions, I think we'll end a tiny bit early. Thank you, Nicolas, for being
well, thank you for giving us the opportunity of talking about that great solution.
It's a pleasure. Thank you very much. And thanks, everybody. Oh, one more question. Is there any common criteria, like evaluation certification plan for ATE ECC 608?
So as I mentioned, we are doing, so we're not planning on certifying the device for common criteria. However, we're doing penetration testing for the 608A, which is one step that is typically early in the process of doing common criteria certification. So we can share the results of that penetration testing with our customers and NDA whenever they actually have they have interest in that question. And that will prove to you that basically the key that is inside the device is correctly protected for the lifetime of the product.
Great. And somebody's asking for a clickable link. So I'm going to try to see if I can post that in the chat. Let me do that. ATECC 608A.
GCP IoT Core.
Microchip ATECC 608A GCP. Damn, fat fingers here. Sorry about that. GCP IoT Core. Okay, is that loading? IoT, GCP IoT Core. Let me verify that link here, and I'll posted in the chat. GCP IoT core. Okay, we're here. So how do I share this here? Is there a chat? Chat, presentation. Is that working for everybody? Let me know if you have a problem with the chat. So that's answered. Oh, here we go. Okay. Cool. We're at the end of it. Thank you very much. Great audience. Actually, there was quite a lot of people watching. That's cool. And we hope this will give you ideas. And more importantly, we hope you'll secure your next device.
Looking forward to talking to some of you soon.
Thank you very much.
Thank you.
Have a great day. Bye.